Okay, so today we move on to this topic on planning. So, in the next 6 or 7 lectures, I will cover a little bit of planning and a little bit of constraint satisfaction, which is I think enough for a introductory course on AI. But next semester Dr. Narayan Swamy and I are offering a course on planning and constraint satisfaction, which will go into much more detail in the topics. So, what we are doing here is just the basics, but the more recent advancements we will probably do in that course essentially. Now, planning is, if I, so there is a nice book on planning which we are not following here by Malik Galab and Dina Now and Paulo Traverso, called Automated Planning, and they start the book by this definition of planning, and they say it is the reasoning side of acting. So, planning of course is concerned with actions essentially. We have not dealt with them explicitly, on and off. For example, we looked at heuristics for the blocks world, we talked about moving blocks around, but we did not really explicitly model domains and we did not explicitly model actions, and we will do that in the planning part that we are doing now. Now, just imagine an agent. So, this is world and the agent inside the world, but we will draw it here. He perceives the world and presumably deliberates and then acts. So, this is a model of an agent in an environment that we have, that the agent perceives the environment or the world, does some deliberation or some reasoning as Gallup and all call it, and then based on that reasoning the agent does acting in the world. Of course, we as human beings do it all the time, we are planning consciously or unconsciously. Our whatever we do, these are not random actions that we do. Almost everything we do has a certain goal in mind, and we think about how to achieve that goal, and our actions are oriented towards achieving that goal essentially. So, goals of course can be long term or short term and things like that, but all the time in the world we are planning. Now, of course, in the world of computing, planning is becoming more and more important as systems are becoming more and more autonomous. So, for example, you must have heard about autonomous cars nowadays. So, there is a Stanford car, and in fact, there is a car rally for autonomous cars. So, you have to let loose a car in some sense and it should be able to go to a destination. Now, if you think about what is involved here, it is not just route finding, which is what we have discussed to some extent, but to drive a car there are many actions that you have to do. You have to look out for other cars, you may have to swerve, you may have to brake, you may have to accelerate or decelerate, all these are actions, and somebody has to decide, or some agent or some program has to decide which actions to be done at what time essentially. And that decision making or this reasoning side of acting is what planning is all about essentially. So, we imagine that we have a planning system and that interacts with what some people call an executive, which interacts with this world essentially. So, I am using the term executive, it was used by NASA in one of their early systems, the remote agent architecture. So, you should look up on the web about this remote agent. It was an experiment done by NASA in experiment called Deep Space 1, sometime in the mid 90s, they had this aircraft flowing, spacecraft flowing somewhere in space, going towards some asteroid or some planet or something. And in between for 2 or 3 days, they had removed ground station control from that spacecraft, which means they had let it function autonomously, deciding for itself what it would do in the next 2 or 3 days. And during that period, they had also introduced deliberately a fault in the spacecraft, and which was used to testing their automatic fault diagnosis system, which of course, we are not doing here, but apart from fault diagnosis, the planning was an experiment that they did. Then you must have heard about Mars rovers and the more recent rovers that have been sent to Mars. Given the fact that it takes of the order of 20 minutes, I do not know the exact figure, for a signal to travel from Earth to Mars, you cannot control a vehicle on Mars as you would be controlling a vehicle, let us say in your lab, if you had a remote or something like that, because the signal takes that much more time. In such situations, it is inevitable that you have autonomous planning built into the system. So, both in the remote agent architecture and in the Mars rovers, what the scientists do is that they give high level commands, go and explore that area or go and collect samples of this from this area, and then the rest of the activity is planned by the system on board. So, planning, of course, these are sort of extreme examples, space examples, but planning happens all the time essentially, scheduling, holiday planning, you go to some flight reservation systems, they will tell you that if you want to go from here to Brussels, what are the flights you should take. So, all this comes under planning in some way or the other essentially. So, let us look at this model of what is happening in the world, and let us see to what degree of complexity we can capture this essentially. Okay. So, in planning systems, we are going to do the following. We are going to talk of domain description, action, let me use the word specification, or action description, describing what actions are available to you, and of course, goal states. We will look at this in a little bit while. The early planning systems were kind of domain specific. People would say, okay, I want to build a system for planning in this domain or planning in that domain and so on, but following the theme that we have been in this course, which says that the problem solver must be removed from the domain, we want to find general purpose planning systems, or as this community calls it, domain independent planning essentially, which means that we will devise a language to express all this. So, this is like the domain functions that we talked about in search. The planner would be independent of this. You would write the planner assuming that you would read a domain description and a problem description or goal description, and the planner would automatically compile and run essentially. So, one of the earliest planners that was built was called strips, and we had possibly talked about it, at least in the context of this robot called Shaky. So, if you remember, Shaky was one of the earliest robots that was built in the computing community, which could roam around the corridors of Stanford University, maybe looking for PowerPoints and things like that, where it could charge itself. It had a onboard camera and it was on 2 wheels. So, if you just look up Shaky, you will see some photographs, and I had shown the photograph during my introduction as well, and it was a fairly autonomous camera. Of course, it could not do much, it could just roam around the place, and the planner that they used was called strips, and strips, some people say, stand for Stanford Research Institute Planning System essentially. and that was the earliest planner, that was the earliest kind of language description, the simplest kind of language description that you can use for planning. And we will sort of look at this language to start with essentially. Now, to do all this, people have started working with devising languages. So, these are called planning domain description language, or in short PDDL. And there are versions of PDDL. We start with PDDL 1.0, and we will look at only PDDL 1.0 here in this course, and which is basically what STRIPS does essentially. So, what happens when you go to higher levels of language? Basically, the richness of the language increases, and you are able to describe the domain as well as actions of more complex nature. So, let us see what are those kind of simplifications that we are making in scripts. So, we are describing scripts domains now. So, it is a term that has become common to use for the simplest kind of planning domains. We call them scripts domains, because that is what this scripts planner use essentially, and I will describe them in a short while. So, these are the simplifications that we simplifying assumptions that we use. One is that the space is finite. So, you can still work with this idea of state space search that we started this whole course with, where you are in some given state and you want to be in some desired state, and the actions that you have to choose. Only now we will. So, that time we said there is a move generation function which takes a state and gives you successor states. Now, we are saying that we have access to actions and we will reason with those actions essentially. So, the simplest assumption is that the state is finite essentially, the state space is finite. The second assumption that we make is that it is fully observable. Which means, just as we discussed when we were talking about games, we said we have complete information games and incomplete information games. A fully observable planning system is one where the agent can sense the entire world, which means this perception part of the agent is perfect. The agent can see the entire world and there is no missing information essentially. Each of these assumptions that we are talking about, we can relax and we can get richer in some sense planning problems or planning domains essentially. The third is it is static, and by static we mean that the agent is the only one making changes in the world essentially. So, there is no other influence in the world, all this is not allowed. There are no clouds, there is no sun moving around, there is no rain falling, nothing. Agent is the only one which is making changes in the world, and such a domain is called static. Obviously, when you talk about multi-agent systems, adversarial systems like game playing that we saw, then this domain this assumption we are violating, and then the problem becomes more complex essentially. Then the actions are deterministic. All these are simplifying assumptions that we are making, and what do we mean by this? That when an agent does an action, let us say pick up this watch essentially, or pick up this remote, whatever action the agent does, it happens in the real world as planned essentially. So, which means in a deterministic world, if I were to say throw this ball into the basket on a basketball court, then it would go into the basket essentially. Of course, the real world is not deterministic. When you play basketball, you would have realized that it needs a considerable amount of practice to get better at it, but we will make the simplistic assumption that the world is deterministic, which means that whatever actions agent does, the they will happen in the real world essentially. Just imagine that what would happen if the world were not deterministic, then you create a plan that okay, you will get out of this building, you will board your bicycle and go off to the hostel and have some tea, and then when you go down you find that somebody has stolen your bicycle, or maybe the bicycle is punctured or something like that, then you can no longer do the plan, which means. So, the effect of deterministic action is that once you plan, your plan can be executed without any flaws essentially, because the world is fully observable and static and deterministic. If you make a plan, the plan will execute in the world. So, you do not have to worry about monitoring the plan and things like that essentially. So, nowadays of course, there is a big community looking at stochastic actions or probabilistic actions. Also, you must have heard about probabilistic planning. So, they follow an entirely different approach to planning. What we are doing is something like search, they do something which is quite different. So, we have this Markov decision processes and so on. Dr. Ravindran talks more about such things in his course. I think he is also offering a course on probabilistic reasoning next semester. Okay. Then simple goals. By simple goals, I mean that we have the goal test function is applied on the final state essentially. You say that this is what you want to achieve. You want to be in the hostel and you want to be eating a dosa and having some coffee, and if that is the situation, then the goal is satisfied. So, that is what we will call as simple goals, goals tested only on the final state. As opposed to this, there is a community. So, if you look at higher levels of PDDLs, for example, they would talk about what we call as trajectory constraints, which means you have conditions on the path that you are finding for the goal essentially as well. So, the trajectory is the solution and you have conditions on the solution essentially. So, for example, if you are planning a long trip, you might say that at all points I must be within 5 kilometers of hostel. For some reason, let us say your friend is not too well and or susceptible to something, and you say that my route must be such that at all points I must be within 5 kilometers of a hostel. So, that is a trajectory constraint. You may be saying that I want to go from here to Nagpur, that is the final goal, but I have constraints on the path as well. We will not look at those, we will only look at simple goals. Or you might have constraints like every time you go into a room and out of the room you must switch off the lights or something like that. No, these are constraints on the path essentially. Also, soft constraints. Our goal description is rigid, that only if those conditions are met we will say that a goal has been achieved essentially. Whereas, you might have soft constraints or soft goals which might say okay, I would like to go to the market and if possible I want to go and see a movie and buy all these stuffs and do some, you may have a plan, but you may accept a plan which does not achieve all the goals completely, but achieves as many as possible for example. And then you would have of course have a penalty associated with that, saying that okay, if I do not achieve this goal of buying a toothpaste, my plan is not as good as the plan if I had also bought a toothpaste, and then it becomes an optimization problem, because you have to now find a plan which satisfies certain optimality criteria, as opposed to just satisfaction criteria which says if these things are true, then I have achieved my goal. Whereas, here you are willing to relax it, and that is why it is called soft constraints, that you are willing to allow for some things not to be achieved and you would still accept a plan essentially. So, obviously, with each such condition being relaxed, the problem becomes harder and harder essentially. Then a plan is equal to sequence. of actions. We will assume that a plan is a sequence of actions, and we do not want more complicated plans which are networks of actions and things like that. And one more constraint which is very important, which is being relaxed quite often nowadays, which is the notion of time. So, we will assume that we do not have a notion of time to start with. We will just say action A happens, then action B happens, then action C happens. There is only a notion of sequence, that actions happen in a sequence, whereas in the real world some actions may take more, some actions may take less amount of time. So, you may say I will take a bath and have a cup of tea and then cycle to the gate, and each of these actions may take a different amount of time. If you want to take that into account, then you have to have what we call as, so what we have is instantaneous actions, but what we can have is, so I will just write versus durative actions. So, by durative actions we mean actions which have durations, and then of course, you have to, you can even start talking about doing things in parallel once you are talking about time and duration. So, you can say that while my sambar is being cooked on the left side gas, I will make something else on the right hand gas. So, two things will happen in parallel. This will take so much time and this will take so much time, and then you might worry about what is the total amount of time that my plan will need to execute, which is called make span in planning terms. But durative action brings these kind of situations. So, one interesting problem which was raised by a PhD student from one of these universities, I think Washington University, is the following. He says that, and this was a problem which could not be solved by the techniques that were there till 2007, and it is a task of repairing a fuse essentially. So, it is a very simple problem. Let us say this is the duration, whatever time t you need to repair the fuse. So, the situation is that lights have gone out into your apartment and you are repairing the fuse, and it takes you that much time. So, the action is durative, it means it takes that much amount of time, and you have one matchstick essentially, and the matchstick can give you light for so much amount of time. So, this is along the x axis. So, y axis is meaningless, basically this is a interval over time. So, this takes so much time, this takes so much time, and the task is to repair the fuse, and but you need light when you are inserting the fuse into the socket. So, essentially this matchstick must be lit in such a way that it overlaps with the end part of this fuse repair action. Now, the trouble with this is, unfortunately we are not going to go into details here, but the thing is that when you are dealing with durative actions, you cannot talk about time going in seconds or something like that. That would become simply unmanageable essentially. So, you do not do that. What you do is you say, okay, can I do anything at this time point when I am starting this action? Maybe I can start another action or something like that essentially. Can I do something when this action is ending? So, time jumps from beginning of action to end of action essentially, and then you plan to do something there. Now, the whole problem with this is that you cannot reason about it here, you cannot reason about it here, you have to sort of reason about it in such a way that this comes into here. So, this gave rise to some very interesting problems in how to build systems which will do. Now, of course, we have planners which can do this, and they would place an action somewhere in between, so that this straddles this essentially. So, durative actions of course increase the complexity manifold essentially. So, one way that some people have tried to model durative actions is by saying to splitting it into two actions, with saying this is a start action and this is the end action essentially. but derivative actions will have conditions like something must be true throughout or something must be. So, for example, if you are taking a bath, then you might have this condition that the light must be on throughout, that you are afraid of the dark or something like that. And at the, or if you are traveling from place A to place B, then at the end of the action you should be at place B, at the beginning of the action you must be at place A, and in between you must be at neither place. So, these kind of constraints on actions make complexity of planning more and more difficult essentially. So, the strips domain. So, I should say here in some sense cross. So, we are not using derivative actions in strips domain. These are the simplifying assumptions we make in strips domain. Actions are instantaneous, the world is fully observable, actions are deterministic, the world is static, and we have simple goals. Even in this simple domains, it was shown to be p space complete. So, planning is one of those hard problems that you are trying to solve, and it will always need some exponential amount of time essentially. Every time you relax these constraints, the problem becomes more complex in terms of this thing. So, let us look at how strips describes actions. So, we will use this blocks world, we already talked about blocks world, moving blocks around. So, we will see how blocks world is described in strips essentially, and PDDL is basically a kind of a standardization of what we are seeing here essentially. Okay. So, first we have domain predicates. So, for example, we might say on x y, where x and y are variables, to signify that block x is on block y. Then we can have I will use the ones used in strips. So, on table x, then holding x. We assume that there is a one armed robot which is moving the blocks around. So, that one armed robot can hold one block, and that is described by this predicate saying holding block x. So, this x y would be filled up with variable with constants in a real world, in a real problem essentially. Clear x says that there is nothing on top of x essentially, which is a kind of a short form for saying that it is not the case that there exists a y such that on x on y x. So, we will look at first order logic a little bit later in the course, in case you are not familiar with the language. So, on x y on table. So, these are the four. So, whenever you define a domain, you have to first define what are the predicates which will define the situation essentially. So, instead of saying that we have some state representation, now we are saying that you must define the predicates which describe the state, and the state will be a collection of such sentences. So, for example, if I have a situation like this A is on B, it's on C, F, something like this, then I will describe it by saying on AB, on BC, on ED, on table C, on table D, on table F, clear A, clear E, clear F, and this is my one arm robot. I need a predicate for that, which we will call arm empty. So, either you are holding something or the arm is empty essentially. So, we can describe this state using these predicates essentially with plugging in values for the variables essentially. And then we have the operators or the actions. So, in this simple world we will assume there are 4 actions. One is pick up okay. So, in PDDL you first describe what are the predicates that you will use to describe the world, then you describe actions. Now, actions are described by 2 things. One is what is necessary for the action to be applicable, or what should be true for the action to be applicable, and secondly what will become true after the action is applied essentially. So, in some sense we have the left hand side and the right hand side like in the rule that we talked about earlier, but in this strips kind of a thing we would say that there are 3 lists. One is the precondition list, one is the add list, and one is the delete list. This is the original way in which strips describe the actions. So, precondition list is those predicates which must be true for the actions to be applicable. So, if you want pick up x to be applicable, it should be true that it should be on the table and it should be clear, which means nothing must be on top of it, and I will just use for this A E and R must be empty. So, if these 3 predicates happen to be true in my domain, which means of course, I have to just see that the precondition list is a subset of my state description. The state description is a set of predicates which is describing these things essentially. So, for example, this will have on table F and it will have clear F and arm empty. So, because these things are in the state description, this action becomes applicable, that I can pick up F for example.
You don't need on table.
That is a way that strips original description is given. So, if you look at any textbook we use that. We will distinguish between the 2 actions in which we pick up something from the table and we pick up something from top of another block. So, that will have a different precondition, just to illustrate what is happening. Well, it has to be on something, either on the table or on another block. So, this pickup is only for picking up things from the table. So, the add list as they used to call it is a list of effects which will become true if this action were to be executed. In this case, the only thing we have put is that the robot will be holding this block X, and the delete list contains those things which will become which were true, but which are no longer true, and that includes things like on table X and arm empty X. It also include clear X, but as I will discuss in a moment, you can either write it or you can ignore it, it does not matter. So, corresponding to this, I have an action called put down. So, whose precondition list says holding X, whose add list contains on table X, arm empty. Now, if I want to remove this clear X from here, then I should add it here. If I do not remove it, then I should not add it here. So, you just think about this, that either I must add it in both these places or I can leave it out of both these places. What is important is that if you are picking up, there must be nothing on top of it. So, I need this clear X at that point. It is obvious that once you pick it up and put it down on something else, there will be nothing on top of that at that instant. So, clear x will remain true after that essentially. So, okay, holding x. Corresponding to this, there are two more actions when you have, which we call as unstack Okay, so, I will just name the actions or operators and I will expect you to describe them in more detail with this 3 lists, precondition list, add list and delete list. So, the only difference between unstack and pickup is that pickup is from the table and unstack is from some other object. So, you can unstack A from B or you can unstack E from D, and the conditions are similar. A must be clear, A must be on B and arm must be empty to unstack it, and likewise you can stack it essentially. In the more modern PDDL language, I would call this as positive effects. So, if my action is A, then this list is the precondition list of A. This is the effects positive of A and this is the effects negative of A. So, in the modern PDDL language, we do not use this names precondition list, add list and delete list. Instead, we say preconditions and effects can be positive or negative. Positive means they become true after the action is applied. Negative means that they become false after the action is applied, and the two of them together is called effects. Okay, so, we describe a set of actions using the precondition list and the effects list of the actions, and we can basically now have a language to define any domain in which we want to do planning. And what we will need to do is to define a set of predicates which describe the domain, which means describe the states of the domain, and then define the actions which can be done essentially. So, what is a planning problem? A planning problem is defined by a set of operators or actions, a domain description, a start state and a goal description essentially. So, this is the start and this is the goal. So, for example, this could be my start state. I have not written it in this language, but you can write it quite easily. My goal description could simply be something like I could say on this could be my goal description. So, observe of course, that I do not need to completely specify the goal as a state. The start state I need to completely specify. We said that it is fully observable, everything that is true must be given, but a goal does not have to be completely specified. Your goal may simply be that as long as those two things are true, then I am happy with my plan essentially. I do not care where the other blocks are, as long as E is on C and C is on F, then I am happy. So, E is on C, C is on F. This F could be on something else or be on the table, and I do not care about the rest. Now, of course, this is like what we do in the real world, we do not necessarily describe the goal completely. You just say this is what I want to be true, I do not care about anything else essentially. So, the goal description is a set of predicates, the start description is also a set of such predicates, instances of predicates. When do we say that an action A is applicable? If precondition of A is a subset of start. It is just like saying that if my preconditions are true, then well S does not have to be start, it can be any state. Okay. So, an action A is applicable in a state S if its preconditions are part of the state essentially, which means that they are true essentially. We say that when the action is applied, we get a new state. So, we progress new state S prime, where S prime is given by the given state that we are in. I will use this as a minus sign, or I can use the standard minus sign, whatever. The effects minus of A union effects plus of A. So, once you have defined a state and once you have defined an action, we know that if an action A is applicable in the state S, then I can apply action A to state S to go to a new state S prime, which is given by I remove everything which are the negative effects of this action from the state and add all the positive effects of the action from the state. So, I get a new state S prime. A plan pi is a sequence of actions. So, we have assumed here that our plan is a simple thing like a sequence of actions. So, our plan, we will use the term pi, is a sequence of actions A1, A2, An essentially. So, the first thing you want to do is to write a small routine which will validate a plan, that this plan is doing my task. What is the task? The task is I have been given a start state, I have been given a goal state, and somebody tells me that this is a plan, somebody meaning some program that I have written tells me that this is a program, this is a plan, and should be able to validate that this is a plan. How do I do that? Before we do that, how do I do goal test? How do I say that a given state is a goal state?
Predicates are true.
Are true, which means, so goal test is simple. G should be a subset of a state S. The G is a set of predicates describing the goal. So, if G is a subset of S, then that S is a goal state. S is a state, it describes the whole state. G is just some conditions I have said on this on the state. So, it is like saying that I should be sitting in the canteen and having a dosa. I do not care what everybody else is doing. If that is true, then I am in a goal state essentially, and that we can test by simply doing a subset check essentially. So, now having a goal test function, how do I, and somebody gives me a plan pi, how do I know that the plan is a plan for solving the problem? I must be able to write a small program to validate that. What will that program do? It will progress over the state. So, it will apply first action A1 to the given state, then in the resulting action it will apply A2, which means it should check whether A2 is applicable and apply A2, and then keep doing that till we apply all the actions, and then in the resulting state that we have progressed to, remember this, we have this progress operator, how can we move from state to state? That last state must satisfy that condition that the goal must be a subset of the states. Okay, so all we have done today is to describe the planning domain, so to speak. The planning domain is described using a language called the planning domain description language, and I urge you to look at some website which will tell you what, which will give you the actual syntax of PGDL. But essentially it constitutes of a set of predicates which are used to describe the domain or define the domain, and a set of operators or actions which are the actions that you can do in the domain, or the real actions are the instances of these operators, if you want to distinguish between that. And then you can describe a planning problem by saying this is my start state. So, I can say on AB is true, on BC is true, on ED is true, on table F is true, on table D is true, on table C is true, clear A, clear E, clear F, and arm empty. If I state all these things, I have said I have described my start state, and I say my goal state is that C must be on F and E must be on C, and that is my goal state. So, I can now have a goal state. Now, all I need is an algorithm to find a plan, and then of course, I also need to be able to validate the plan. We will see that some algorithms will need this validation check, because it can produce plans, sequence of actions which are not necessarily plans. So, we need this check essentially. So, in the next couple of classes we will look at a few algorithms to find this plan essentially. What is the simplest approach you can think of? Sorry?
Write everything out and arrange it.
No. You are talking of a specific problem which is the blocks world domain. Now, this is just to illustrate, this is just we are using as an example to illustrate our planning algorithms. Our planning algorithms have to be domain independent. We do not know what are the predicates and what are the actions, but we should be able to still write an algorithm to do that. So, his solution of course is a very nice solution which sort of defies the fact that I kept saying it is p space complete, but in fact in the blocks world domain there is a very simple algorithm which says first put everything on the table, which will take you, if there are n blocks, at most some order n by 2 or something like that, or order n, let us say. Just I put everything on the table and then assemble the thing that you want to assemble. So, you want C to be on F, pick up C, put it on F, you want E to be on C, pick up E and put it on C. So, it can be done in linear time essentially, but that is a very specific solution to a very specific problem. What we are interested in is in domain independent planning, which means we do not know the domain, we do not know the predicates, we do not know the actions, but we have a language to describe the domain, the predicate and the actions and the start state and the goal state, and then our algorithm should be able to operate upon that. So, the simplest approach, as you can guess, is the forward state space search that we have been doing all this along. Go to the start state, apply the move gen function. How can you write a move gen function here? You have to simply test for all the actions which are applicable, and they will basically constitute your move gen functions. They will give you what are the actions you can do. Keep doing that, and then we also have a goal test function. So, the simplest is forward state space search, but we will look at other approaches and we will do that in the next class onwards. Okay. So, we will stop here.